Our first speaker, Moni Naor, is going to talk about private partitions or something else according to which slide he chose.
So I guess in the interest of privacy, I didn't send a title, but then I learned that it's not of much use, so there is a title after all. Anyway, so I'm going to talk about private partitions, and this is based on the paper Pure Differential Privacy for Rectangle Queries via Private Partitions, joint work with Cynthia Dwork, Omer Rangold, and Guy Rothblum. So this is the one-slide version of the talk. What we're suggesting is a new tool, certainly inspired by previous work, but we're suggesting it as a tool. You want to partition, you have a range 1 through D. You have points on that range, perhaps several in the same place. You want to partition it into n segments, at most n segments, so that no segment is too large, in the sense that it has at most log D points, log D people. And the partition itself is differentially private. Releasing what the segments are, what are the bins, that will be done in a differentially private manner. And we'll decide on the partition in an online manner. So we get, we're told we're now in time t. Is there any point here or not? And then we decide whether to have a bin, whether the segment ends there. So when we pass a segment, we release it. So this is the one-slide version, and then so the points are arriving. At any point in time, we're told is there a point, or whether perhaps there are several of them, several people are at that point, and then we produce the partition into bins.
You're going to announce who is in which?
No, I'm just going to announce. What I'm going to announce is what is the segment. The output of this process is the segments.
The private information is whether I'm 1 or 5?
No, who exactly, whether a person is in here or not. I'm going to protect, I'm going to say it more accurately, but I'm going to protect whether a person is in the database or not. Isn't this a point, whether such a point exists or not? Is it in the database, is it considered at all or not?
So the condition that we don't want to have too many people in a segment says that the choice of where to put the segments has to be different, is not determined in advance. They will depend on the people. And now you have a privacy issue.
So you can see here that some segments are more dense, and therefore they're smaller, and some are sparser. I mean, as much as the slide allows you. And what do we do with it? We use it for counting in a continual observation manner, and for answering interval and rectangle queries. Okay, so this is a one-slide version, and I'm going to say a little bit more. So, if you're here, you've probably heard about differential privacy. I'm not going to go through the whole thing. From our point of view, we really like the fact that it has nice properties like it's composable, it's quantifiable, and it's provably resulted to known and unknown attacks. And we will be interested in counting queries. How many, we have a database of n people, how many people satisfy a certain predicate P. We're talking about this sort of property, and we would like to answer such queries. This is all well known. And, so the property of the requirement of differential privacy is that for any database DB and any event T, we say that the mechanism A is differentially private, a mechanism that is, it looks at the database and announces something. If the probability, if we look at one particular record, me, the probability that the mechanism has an output inside T in case I'm in the database or in case I'm not in the database, if the ratio between these two probabilities is between e to the minus epsilon and e to the epsilon. So in such a case, we say that the algorithm A is differentially private, if it's true for all databases, for all events T. These two probabilities are close to each other. Right, so in the original paper by Dwork, McSherry, Nissim, and Smith, the way to, a mechanism that achieves this for counting queries was suggested by adding independent noise, by adding Laplacian noise. And the more queries you have, the problem with adding independent noise is that the more queries you have, the more noise you have to answer, so you get less accurate results. If you have only one query, you have to add little noise. After a while, I have to add more and more noise. On the other hand, as starting from Blum, Leggett, and Roth, you can actually answer lots more queries if you have coordinated noise. If you're if you add the noise, if the inaccuracy is added in a sophisticated manner. And the error is more or less proportional to logarithmic in the number of queries. However, the running time is large. They're not, computationally, these are not efficient algorithms necessarily, they depend on the size of the universe, which in the example I give, the universe is D. Could be large. And we want algorithms that are faster. And but unfortunately, there are lower bounds on such things, coming from crypto actually. And in general, we cannot hope to have fast algorithms for answering general counting queries. But who said, I mean, we aren't necessarily interested in arbitrary queries. There are very structured ones, and we want to know how well we can answer structured ones. And in particular, here we'll revisit intervals and rectangles and counting under continual observation. So here we think of in intervals, we think of the databases containing n people. Each one has an integer value between 1 and d. And the query is an interval ij, and the query is how many people in the database are in this interval. Okay, so this is the database. This is a query, and you want to answer how many people are in this interval. Okay, so this looks relatively benign, and we want to do it in an accurate and efficient manner, computationally efficient manner. So what we have is a new algorithm whose error behaves like logarithmic in D. D is the accuracy here, and log squared n. And what do we know about this? So this is the new thing. So previously, what we could do was log squared in D, and there is a lower bound of log D. So you cannot do better, you cannot have better accuracy than log D, and the best upper bound was log squared D. On the other hand, let's see, oops, somehow, okay, somehow this disappeared. Okay. So there is an alternative to pure differential privacy, which is approximate, or epsilon delta differential privacy. So remember, in differential privacy, we have this property, the probability that I see a certain outcome, given that given that me is in the database and given that I'm not in the database, because these ratios are very close. In approximate, in epsilon delta differential privacy, we're adding a delta to these things. So delta hopefully is something small, much smaller than epsilon, and the epsilon delta differential privacy in epsilon delta differential privacy, we are giving up this delta. So if it's extremely small, of course, it's good, but what happens if it's not so small? Now, epsilon delta differential privacy has all sorts of nice things. For instance, for advanced composition, you get epsilon delta differential privacy, but we're really interested in understanding the difference between pure and approximate differential privacy in this work. So here, so as I mentioned here, for approximate differential privacy, there are much better, if you look at just at D, there are much better results. So there is an upper bound, which is log, it's really 2 to the order log star D. Log star D is the iterated log. And that's already surprising. Where did it come from? And even more surprising, there is a lower bound by Banissim, Stemmer, and Vadan of log star D. So if you notice, once you give up on the, if you go from pure to approximate differential privacy, the dependency is not logarithmic in D, but either somewhere between log star D and 2 to the log star D. And I mean, I view this as a very interesting question, exactly whether you're in the 2 to the log star D or in the log star D regime. Well, obviously, these numbers are extremely small for every value you can imagine. But still, often when we see such expressions, there is something hidden here, and it's good to understand. But I'm not talking, in this talk, I'm not in this world, but in this world, in the pure differential privacy. And here, we cannot do better than log star D. We have a lower bound that you have 2 ways. This is from the work Naor, Pitassi, and Rothblum. You have to your inaccuracy has to be log star D. Cynthia, do you?
What do you know about the computational difficulty of the to the log star D?
But I don't think that there is. I mean, the algorithm is reasonable as far as I understand.
It's nearly linear.
Yeah.
Fantastic.
Nothing. Nothing. Yeah. So you could view it as an advertisement for approximate DP rather than what I want to talk about. But I want to talk about pure.
The delta under that, you don't provide that? Does it impact on?
It's small. I mean, it's where does the delta come in?
So in the sorry, I
Yeah.
can answer. In the upper bound, there's going to be a multiplicative log 1 over delta, and then in the lower bound, you can show that such a dependence of log 1 over delta is also necessary.
Log 1 over delta.
Yes.
So that'll beat log star D most of the time. Yeah?
Yes.
Okay.
What you're stating the result.
So what what I'm going to talk about falls in between these two. So we had an upper bound of log squared D, we had a lower bound of log D, and the question is what is the right answer? And okay, and then some generalizations. Okay, so how is the upper bound? What is the upper bound based on? The log squared D upper bound based on? You partition. You think of it as each point as being. Think of the bit representation, or think of it partitioning the full universe into segments, fixed segments, and what you're going to do is you're going to count for each one fixed segment. You're going to count how many points, how many people fell in that segment. And if you notice that once you're given a particular query or an interval, you can compose it from up to log segments and get the answer. And on the other hand, no point is in more than log d segment. So this means that your sort of epsilon that you have in order to answer regarding these very nice segments, these epsilon prime has to be smaller by a factor of log d. Remember, we're in the pure case. And the inaccuracy behaves something like this, like log squared d over epsilon, when you add things up. So this is how we get to log squared, and it doesn't look like exactly the right thing you should do, because obviously some segments are very sparse, some segments are more populated. It doesn't make sense to treat all of them in the same manner. It makes much more sense to concentrate on the important segments. But of course, reporting the important segments in itself is violates privacy. So so this is the answer. So this is where we go back to what I mentioned at the beginning, the private partition. Okay, the other type of queries are a generalization of rectangular queries. Here the points are some vector in C dimensions, and a query is a rectangle, I1 defined by I1, J1, I2, J2 up to IC, JC. And the query, the natural query, is how many people are in that rectangle. Right. So this is a query now, and we have to answer 5 or something close to 5. And clearly, I mean, it's not hard to imagine how you generalize from answering intervals to answering rectangles. And what we can do is we have an algorithm where the error behaves like log d times c squared, so which is probably small, it's really log d, times log to the 1.5 c plus lower order terms of n. So like before, we have it, it doesn't quite generalize as before, it's slightly worse than what we do for intervals. You think about it, and the runtime is linear in n times smaller polynomial factors. And here, before you had to pay a price which was worse in terms of d, it was log d to the order c, and the runtime. And there is a lower bound that the dependence that it has to behave like log n to the c. Even that's, in this case, it's true even for approximate privacy. So here we don't have such a dramatic difference between pure differential privacy and approximate differential privacy. Okay, and finally, counting under continual observation. So what we want to do is we want to monitor the number of events over d time periods. So we have like a web counters, and we are monitoring the number of clicks, and we want to keep the fact that Cynthia clicked on a certain website, on a certain link. We want to keep it as we want to keep it private. So we're talking about event level privacy. We're not trying to protect all of Cynthia's clicks. We're only trying to protect the particular one she had. And you can think of it like an example would be Google Flu Trends, where you want to know according to searches, in this case it's search words, you want to know whether to predict a flu epidemic or not. So you want to be able to see how many people searched flu-related items. I think that nowadays the idea that this is a panacea and you could really predict flu from these search words is debunked or not considered to have strong evidence, but it's still obviously a helpful tool for something, if not for flu. So, right, so we have a stream, it's a 0-1 stream, it's relatively sparse. Most of the places are 0. And from time to time you have a 1. And we want to have a publicly observable counter approximating the total number of 1s at any point in time. So we have to know how many people have viewed a certain YouTube video. We want to we want to have a good approximation of the number of people who watched a certain video, who clicked on a certain, or searched for a certain keyword, or whatever. Okay, so the output has to be continuous. And what we're hiding is the individual increments, and of course, want reasonable accuracy. So these are the 3 applications. And here, what we can do is, again, like in the interval, I mean, they're very related, obviously. You can view it as a certain type of query from 0 to 1, except that here it's clearly online. The accuracy we have is log d plus log squared n, and as the proof, the lower bound proof follows here as well, so you cannot do better than log d, and the upper bound from before works, it's log squared d.
What is n here in the continual observation?
Sure, n is the total number of the actual number.
D is the range.
D is the range.
Okay. Okay, and then it's the count.
Yeah. So total number of people who are going to watch this movie, let's say, I don't know, 300, 100, whatever, and that's n, and t, and d would be the total time until eternity. Okay. So the tool I mentioned is private partition. So we have points. When the points arrive, we only know about the person when they arrive. We don't know about them before. And we have to output the partition in an online manner. Okay? As in here. This is what we're going to do. And then that's going to be our main tool, and then we do, if we do that in a private manner, then the rest will be using older algorithms. We'll simply be using older algorithms to output answer the intervals, answer the rectangles, do the continual observation, whatever you want.
So here the n now is segments, not people.
No, okay. N is the number of people, and I'm saying that the number of segments would be at most n. I don't know. I don't need to know n in advance. So the number. So I don't have more segments than people, and no segment is too populated. That's the promise. So it's quite clear to go from partition, once I have this partition, to go to answer interval queries. Really the n segments are the new universe. So I've really translated the universe from size d to size n. And then I use, so I know that no segment is too large, so I don't have a large error because of that. And then I build on top of that segment whatever I did before. And whenever I had a d, I can plug in an n. That's why we have a log squared n, say, not something smaller. But I got rid of the d. I have only log d and not log squared d. Right? And what do we do with respect to rectangles? The same thing. We partition each axis into n segments. So we work on each axis. The new universe is going to be of size at most n to the c. So no segment is too large, which would mean that we don't have we have only a small error, and then we'll add it up and make sure that things are okay there. Okay, we do that for this, and then we do it here. I mean, of course, we can do it simultaneously. Here, there isn't the issue of online and getting points online, and then we answer accordingly. So we're reducing the universe significantly to the size and to the c. And so what do we do? Well, obviously, we have lots of tools at our disposal. We first have the Laplace mechanism, the good old Laplace mechanism, which is often inside many of the algorithms. For instance, inside multiplicative weights, we do have, we are using the Laplace mechanisms as well to decide on various things. So, in the Laplace mechanism, what we have given a query Q, it's a counting query. What we do, we take the accurate answer and we add noise distributed according to Laplace distribution, the double geometric distribution. And in counting queries, we think of the sensitivity as being 1, and therefore, Laplace noise with these parameters satisfies epsilon 0 differential privacy. Now, what happens if we have k composition of such things? Well, it's not worse than epsilon 0 times k, right? That's the very nice thing about differential privacy of the composition. And we have, if we are going to the approximate world, then the deterioration is on the square root of k. That's, as I mentioned, this is one of the advantages of the approximate differential privacy, is that you have better, nicer composition at the price of cost in delta. But in our case, well, we want pure differential privacy, so it's not, we cannot use the advanced one. So here is the, what is the idea behind the private partition algorithm? Maybe I'll talk about it here. So at any point in time, we have the points that they arrive. So we are going to have one segment which is open. The past is past. I mean, the segments that we have decided on them, that we've decided that the segment is between I1 and J1, and this is the segment, and this is, and we're past the point to J1, then we're done with that. So at any point in time, we have one segment that we haven't decided on the other, on its endpoint. And remember, we want the segment to have at most log d points. On the other hand, it's clear that we should definitely, that if a new person arrives, this shouldn't be a reason to close the segment. Because otherwise we are revealing information about that person, about that individual. So the fact that an individual arrived where at time j, a person, we learn that there is a person at point j. This shouldn't make us close the segment at that point with a particularly noticeable probability. That would definitely not be differentially private. So we have to have a mechanism that decides, whether to close or not. And that mechanism should be very insensitive to the precise number. So here, the idea is that we'll use the sparse vector technique from, I guess, DNPR that I mentioned, and we'll decide on, we'll have a noisy threshold to decide. So what we'll do is we'll decide on a threshold. The threshold would be around log d, because we want at most log d points. So we decide on the threshold. The threshold says we want this many points. But we cannot, I mean, if it's a fixed threshold, obviously it's bad because we'll always output, the end of the segment will always be at a point, at a particular person. So it certainly cannot be a fixed threshold, so it has to be a noisy threshold. Now, what happens if we decide at any point on the noisy threshold? Then we have too many decisions because we have then we have the problem with the composition. So we cannot decide, we cannot choose the noisy, we cannot have too many noisy thresholds. So we're going to have both. We're going to have a noisy threshold and then we're going to have a noisy count. And the noisy threshold is going to be fixed throughout the lifetime of the segment. And the noisy count would count how many points we have in a noisy manner. So we start, of course, the count is 0. And here we choose the noisy threshold. So it's going to be, let's say, 3 times log D plus Laplace noise. And then we are in the ith time period. We add to the count the number of points we had so far. Now we have the noisy answer. The noisy answer is CI. And we compare it to the threshold. If it's more than the threshold, we sort of flush. We decide, yes, this is we seal the current segment. We're saying this is the end of the segment, and we're out. And then we'll restart. We make the count 0, and we choose a new noisy threshold. If not, we continue to the next one. So this is the algorithm. And we do that for any point. So if you look, so why is it accurate? Well, why would you think it's accurate? We have a threshold. You don't expect to see things way more than the threshold. Nothing here. Nothing here is too dramatic. I mean, to be way away, we don't have that many thresholds, so we don't have to worry about. We choose only n times. We choose the threshold. They have to convince you that it's indeed n times, but I think that's also quite clear. We choose this point. We execute this point at most n times, if there are at most n thresholds, so we don't have to worry about this. And right here, this we execute more frequently, but if you're if you have more than log D points, you are going to be above the threshold pretty. Once you're around 3 log D, the Laplace noise cannot put you below the threshold too frequently. So you don't expect to see much more than 3D points. Once that happens, it's just going to this condition is going to be satisfied, and you are going to seal and move to the next one. So, so the reason we didn't have a problem is that we are not going to use the composition. We're going to have a privacy loss only on updates. We sort of don't have any privacy loss when we don't do the updates. So we don't have D privacy losses. We have only N privacy losses. And so therefore we pay only for order N applications of Laplace. And again, why do we think you don't expect, given that we have a threshold at 3 log D, we don't expect, it's going to be very infrequent that we have a completely empty, it can happen that we'll have an empty an empty segment. No one is in that segment, yet it was sealed here. But that's a very rare event. You had noise. These two Laplace noises had to be larger than 3 log d. That's just something that's going to happen only rarely when you're moving, like when you have across these steps. And so we're not going to have empty ones. Therefore, we don't have more than n steps. And on the other hand, as we said before, we don't have segments which are very heavy, which have much more than log d elements. So we satisfy what we wanted. Not too many segments. No segments is too heavy. So once we have the counter, you can ask what you can do. You can do lots of things. It's inside. You can put it inside a lot of algorithms. For instance, you can do, general speaking, event level pan-private continual output algorithm for any low sensitivity function. You can use the counting algorithm in order to get it. You can, for instance, follow expert advice privately, right? Or all the expert type algorithms where you want to follow. You have a bunch of experts. You want to follow them, and you want to be as good as you're competing with the best expert after the fact. So, and you don't know, of course, ahead of time who's going to be the best expert, and the question is how to aggregate the expert advice. And really, if you look at the algorithms, what matters to them is how many times each expert was correct. You usually don't use much more than that, plus some noise, etc. So these algorithms fit very well with, if you want to have experts that their advice is private, you can actually do it without by running a few counters, and then there is some issue of the correct data structure, how to do the counters, but you can do that. And again, you get slightly better results than you had before because we're substituting log square d with log d. So, what did we see? We saw differentially private algorithm for these 3 problems with better dependency on d. And actually, the dependency on d is optimal. For all these problems, there is a lower bound of log d, and this is what we achieved. Perhaps your conclusion would be, why bother with log d, given that we have log star d? Let's go to the log star d. That's a reasonable conclusion, but you have the option if you were willing. You know exactly now the price. There is still the question of the exact dependency on n. Is it log squared, or can you go beyond?
I mean, if the log star d has the square root log 1 over delta term.
Yeah.
In reality.
Yeah.
So.
And a massive constant factor.
Hmm?
And a massive constant factor.
And a massive constant factor.
So
Right.
when you say you know what you're
Yeah.
comparing, you should be clear about what you're
Yeah.
comparing.
Okay. And of course, the question is, can we actually get to log n? And so I think that figuring out precise dependencies is actually something you learn from. You learn something by thinking again, revisiting this problem after 4 or 5 years since we worked on it originally. I think we definitely gained something. We did gain some understanding, and figuring out the exact constant reveals structure. That's the whole point of, not the constant, sorry. Figuring out the exact complexity reveals structure, and that's, I guess, the point of such works. Let me finish with 2 advertisements. There is a differentially private school in Israel, in Bar Ilan, in February. These esteemed lecturers, so if any of you students wants to go, I think that this registration is still open, look it up. in February. And let me also advertise my own department, Crypto and Complexity Group. We have lots of people. And if you're interested in a postdoc, if you're a student, you are very welcome to apply. Thank you.
Thank you very much. Are there other questions?
So can I answer a query then of how many people looked at Google Trends flew to this particular date?
Yes.
It seemed like
You ask me how many people were asking Google? Yeah. Yes.
You had to seal it only when I, reached a specific threshold. But
Release in the meantime, the previous number.
No, you can always answer the queries. There's no problem in answering you ask what will happen with something like the flu trends. It will be very infrequent queries. At some point it will go up, and then the segments will become smaller and smaller. It will go from days to hours to minutes.
Think
So-
of it this way, if you've had almost nobody ask, and you say 0 or 2, you're still approximately correct. And when the answers become much denser, then you start sealing things off and reporting that.
So while the segment is open, so do your answers jump, if you like, every time a segment closes?
Oh, you don't like the fact that it's jumpy?
No, I'm just
You
asking
can actually
whether I
modify.
understand.
No, you're right. You can modify it to make it behave more like a counter. That is, at any point in time, it goes up by 1. It's always monotone, let's say. It always goes up by 1.
Like fit of
Yes.
okay.
Yes, you can do, but this is all post-processing.
yeah, but if you want to just this is online time series kind of thing.
Yeah.
Things are streaming in, stock prices. You want to be able to fit models, and I would imagine you'd want some sort of fixed time points.
No, but from the user's point of view, it looks all normal. I mean, I'm not saying it's indistinguishable from real data, but there's nothing. You can make it monotone. You can make it jumps not too high, and it will be fairly accurate for any interval, for any time. And how many people asked in the month of December until today? How many people asked about flu-related things? You can get fairly accurate answers to that.
So if you wanted to implement this in a system, it would be part of a two-step process. One is generate the intervals, and then a second, optionally, is add noise to the counts in the intervals. So there are 2 epsilons involved, and you have a form of the... So the final accuracy is a function of these 2 epsilons, and the big challenge is how to allocate the privacy budget. So do you have a form for how accuracy depends on these epsilons?
No, I mean, of course, yeah, it's a good question. Exactly how to do the precise things. Once you decide, I'm going to answer interval queries. What exactly to do? Yeah, that's definitely worth figuring out.
Do you know the dependence on epsilon or approximate?
The question also then makes sense in the context of Hart-Loftblum. So you're using an epsilon for the threshold, and you're reporting.
That's where this question came from.
Yeah.
Okay, if there are no further questions, thank you very much again for